All right, so up until this point, we've talked a lot about energy and heat, and now we're going to focus on something called calorimetry, which is basically figuring out how much heat's involved when things change temperature. So calorimetry is the process for the movement of heat into or out of a system, whether we talk about it being chemical or physical. So heat, we're going to see, is always measured in joules, which is a capital J. You may see sometimes kilojoules or calories, but for us, we're almost always going to use joules. So a calorimeter is a device used to measure absorption or release of thermal energy. So it can be something as simple as just a styrofoam cup, or we have more sophisticated ones as well. So we indirectly measure the energy change between the potential energy involved with a process that's undergoing, say, in part A here, and then kinetic energy. So when energy is being transferred, which then we can measure in terms of temperature changes. So first off, always keep in mind the law of conservation of energy. So remember that the amount of energy released by one process must be equal to the amount of energy absorbed by the rest of the system, and vice versa. So something that students sometimes struggle with is how water plays into this. So we would have our sample or whatever our system is, and then water would be our surroundings. So when the temperature of water increases, that's because the sample itself is releasing energy into water. So the sample is actually losing energy to the water or transferring it to the water. When the temperature of water decreases, that's because the sample or the system is taking that energy from the water. So energy is going into the sample, so it's absorbing energy. And this should really say from the water there, so I would just fix that on your note packet. So how do we actually show just how many joules of energy are involved with different temperature changes? This is the formula we're going to use, Q equals mc delta T. This allows us to calculate the amount of heat that's gained or lost. When we get later into the year, we'll talk about some other heat calculations that you'll see in your reference tables. For this unit, we're only focused on temperature changes. So this is actually on the back of your reference table and actually shows you the first four things over here, that Q is heat, M is mass, C is your specific heat constant or capacity, delta T is the change in temp. You do need to know how to calculate delta T, change in temp, on your own, which is always final minus initial. I would also be aware of any units. It allows you to pick out what numbers go where in our equation. Heat's going to always be in joules, mass is in grams. Specific heat has probably the most complicated set of units that we'll be using in this, so joules per grams degree Celsius or joules per grams Kelvin. And temperature can either be, as long as you calculate the delta T, the change in temperature, you can use degrees Celsius or Kelvin. So let's look at three different practice problems. One thing is just being able to identify what everything is. So in this first one, aluminum has a specific heat of 0.902 joules per gram degrees Celsius. That unit tells me that that's going to be my constant C, or specific heat capacity. It wants me to tell how much heat is lost. Heat is going to be Q, which you can see up from the reference table. When a piece of aluminum with a mass of 23.984 grams, that's my mass, cools from a temperature of 415 degrees Celsius, that's going to be my initial temperature, to a temperature of 22 degrees Celsius. So this sample's cooling down, it's going to lose heat energy. So once we've identified all the variables involved, we can go ahead and set it up in our equation. So we have Q equals mc delta T. You're going to see here that my mass, M, is that 23.984 grams. C is my specific heat, 0.902. And then delta T, remember, is final minus initial. So I'm going to show my 22 minus 415. Now you can either write it in like this, or we can simplify that down and get that there's a negative 393 degree change. And that makes sense. It cooled, so the temperature did go down. When you plug those three in and get the product, you'll see that it releases 8,502 joules. Okay, and that negative only just means that it lost that heat energy, which we can tell by the decrease in temperature. All right, let's look at another one. This one you're actually going to fix something on here for me because it's talking about heat being gained. So we're going to flip these two temperatures around, which I'll show you in just a second. So lead has a specific heat of 0.160 joules per gram degrees Celsius. So that's my, here's that switch I was going to have you make. That's my specific heat. How much heat is gained? Heat, again, is your Q. When a piece of lead with a mass of 76.5 grams, that's my mass, has a temperature change, and again, we're going to flip these so that it's going to go from 90 degrees Celsius, it's going to gain heat and go up to 300 degrees Celsius. We're going to use those values, so just change that on your packet. All right, so here we have Q equals MC delta T. I'm going to go ahead and fill in my mass, that's 76.5 grams. I'm going to fill in my specific heat, which is the 0.16, and then my temperature change is going to be 300 final minus initial, which is 90. I can simplify that down and show that I have an increase of, or delta T of 210. Right? And then when I multiply those three together, I get a gain of 2,570.4 joules. For regions, you guys can just round these off to the tenths place every time. If you're in honors, you should be looking at significant figures. All right, and our last one, we're actually not going to solve for Q here, we're going to solve for a different variable, which tends to make the math a little bit trickier for students. The sample of water increases by 69.5 degrees Celsius. So it's saying it goes up by that many degrees, so that's actually your delta T. That is your change in temperature. When 24,500 joules are applied, keep in mind that just the joules there is actually Q, or your heat value. So that's going to be Q. And then it wants to know what's the mass of the sample of water. When you go to look at variables, we're looking for mass, we have Q, we have delta T, so what's our specific heat? Most of the time on the regions questions, it's going to talk about water, and it's going to expect that you're going to look on table B. C is your specific heat capacity. On table B, the specific heat capacity of water is 4.18 joules per grams Kelvin. That's the value we're always going to plug in for the specific heat capacity for water, this 4.18. And most of you guys will actually probably have that memorized by the end of the unit. So I'm going to go ahead and plug now everything that I have. That's my C. So I have 24,500 for Q. Mass is X. Specific heat is 4.18. And my delta T is the 69.5. In this next step, I would multiply those two values together. So 4.18 times 69.5 is 290.51. Okay, if you think back to math class, I get X by itself. I'm going to divide both sides by that 290.5. So I can get rid of them, have X by itself. So when I do 24,500 divided by 290.5, I get 84.3 grams. Okay, if you have a lot of trouble, I will show you, if necessary, a little shortcut here. Kind of similar to the density triangle that we talked about, was that middle school shortcut. There is something that can help you kind of rearrange the letters ahead of time. So when we're looking for mass, you can actually do Q divided by the other variables, C and delta T, and that just allows you to set it up so that you can still get to the same answer. Okay, but that's just going to be your preference and what you're going to practice working with. All right, so those are 3 different examples of how we can do calculations involving the amount of heat depending upon our amount of sample and our changes in temperature.